Assalamualaikum warahmatullahi wabarakatuh. We are from Group G, are going to present about input and output for the subject Introduction to Computer Organization. My name is Muhammad Afif Daniel, and I'm going to present about the introduction of IO modules. So IO modules is a part of computer system where each module of interface to the system bus or central switch and controls one or more peripheral devices. An IO module is not simply a set of mechanical connectors that wire a device into the system bus, but it contains logic for performing a communication function between the peripheral and the bus. Okay, next for the external device. IO operations are accomplished through a wide assortment of external devices that provide a means of exchanging data between the external environment and the computer. An external device is attached to the computer by a link to an IO module. The link is used to exchange control, status, and data between the IO module and the external device. An external device that is connected to an IO module is referred to as a peripheral device. There are three type of external devices, three categories. The first one is human readable, which is suitable for communicating with the computer user. Machine readable, which is suitable for communicating with equipment. And communication, which is suitable for communicating with remote devices. Okay, for the human readable, the example for the human readable is for human readable devices like video display terminals and printers. An example of the machine readable devices are like magnetic disks and tape systems. Communication devices allow a computer to exchange data with a remote device, which may be a human-readable device such as a terminal, a machine-readable device, or even another computer.
Assalamu alaikum wa rahmatullah. This is Abdulrahman Al-Kayan, and I'm going to talk about input-output models. An I/O models is a subsystem in integrated circuit that perform the functionality specific to interfacing a CPU to the rest of the system. It can also refer to a configurable switches called I/O relay models for switching the power to an external load. It can also refer to a programmable logic controller that is used in industrial and manufacturing applications for performing functions like motor controls. And now I'm going to talk about programmed input and output. It's one of the three techniques we use for I/O transfer. The other two methods for the same are interrupted I/O and direct memory access. Programmed I/O is a technique or approach that we use to transfer data between the processor and I/O model. If we talk about programmed I/O and interrupted I/O, it's the responsibility of the processor to control the transfer from I/O to the main memory as an input, and from the main memory to an I/O as an output. On the other way, the DMA does not involve the processor. The main memory and I/O exchange their data directly. And that's for my part. Thank you for your time. Wassalamu alaikum.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faiz bin Azwan with the matrix number 1918161. I will be present about interrupt driver input output. So what exactly input output interruption? Is a way of controlling input output activity in which a peripheral or terminal that needs to make or receive a data transfer sends a signal that causes a program or software interrupt to be set at the time appropriate to the property priority level of the input-output interruption relative to the total interrupt system. The processor itself will be enter the ISR, which is interrupt service routine, the activity on the processor itself. Now I'll be explain and present about on how interaction input-output is working on the processor. Firstly, we will start here. The device issues an interrupt signal to the processor, as you guys can see in the diagram here, which is on the hardware and the software part. So it will be start on the hardware phase first, which is on the processor itself. Alright, and then secondly, the processor finish execution the current instruction before responding to the interrupt. Thirdly, the next step, the processor itself will be test for interrupt, determines that there is one or send an acknowledgement signals to the device that issue the interrupt. The next step will be the processor now needs to prepare to transfer control to the interrupt routine. To begin, it needs to save information needed to resume the current program at the point of interrupt. The minimum information required is the status of processor, which is contained in a register called the program status word PSW, and the location of the next instruction to be executed, which is contained in the program counter. This can be pushed onto the system control stack. And the last step on the hardware phase, the person now loads the program counter with the entry location of the interrupt handling program that will respond to this interrupt, depending on the computer architecture itself and operating system design. There may be a single program, one program for each type of interrupt. This information may have been included in the original interrupt signal, or the processor may have to issue a request to the device that issued the interrupt to get a response that contains the needed information. Okay, and then after that we go to the software phase, which is at this point the program counter and PSW, as what I mentioned, relating to the interrupted program have been saved on the system stack. However, there is another information that is considered part of the state of the execution. In particular, the contents of the processor register need to be saved because this register may be used by interrupt handler. So all of this value plus any other state information need to be saved. The next step, the interrupt handler itself next process the interrupt. This includes an examination of sensitive information relating to the input-output operation or other event that cause an interrupt. It may also involve sending additional commands or acknowledgement to the input-output device. The next step, when interrupt processing is complete, the saved register values are retrieved from the stack and restore the register. The final part, the final act, it will be restored to the PSW and program counter values from the stack. As a result, the next instruction to be executed will be from the previously interrupted program. However, in input-output interruption, there will occur a design issue because there will be almost invariable be multiple input-output modules. How does processor determine which device issued the interrupt? So there will be four general categories of that these are in common use, which is the first is multiple interrupt lines, second a software pool, thirdly is a daisy chain, and fourthly is a bus arbitration. So here you guys can see the diagram. On the left side is interrupt occurs after instruction at location N, and then on the right side return from interruption. So let's discuss about this more. The most straightforward approach to the problem to provide multiple interrupt lines between the processor and the input-output modules. However, it is impractical to dedicate more than the few bus lines or processor pins to interrupt lines. Consequently, even if multiple lines are used, it is likely line will have multiple input-output modules attached to it. Thus, one of other three techniques must be used on each line. One alternative is the software pool. When the processor detects an interrupt, it is branches to an interrupt service routine that pulls each input-output module to determine which module caused the interrupt. The pool could be in the form of separate command line. In this case, the operator raise and place the address of the particular input-output module on the address line. The disadvantage of software pool is that it's time-consuming. A more efficient technique is use a daisy chain, which is a third category to solve the design issue in input-output modules, which provide in effect a hardware pool. For interrupts, all input-output modules share a common interrupt request line. The interrupt acknowledge line is daisy chained through the modules. When the processor senses an interrupt, it sends out interrupts acknowledgement. This signal propagates through a series of input-output modules until it gets to a requesting module. The last things could be alternative to solve the design issue. There's another technique which is bus arbitration. With the bus arbitration, an input-output module must first gain control of the bus before it can raise the interrupt request line. Thus, only one module can raise the line at a time. When the processor detects the interrupt, it responds on the interrupt acknowledge line. The requesting module then places its vectors on data line. So you guys can see here there's difference between interaction in input output and programmer input output. That's all from my part.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Naim Imran bin Muhammad Nizar. My metric number is 1917173. And today I will be presenting for direct memory access. Okay, so what is direct memory access? Direct memory access allows input and output devices to directly access the memory through the system bus. Next, less participation is required from the processor. With regards to that, the direct memory access module must use the bus only when the processor does not need it, or it must force the processor to suspend the operation temporarily. Lastly, the hardware used for direct memory access is called DMA controller or DMAC. This is the block diagram for a DMAC. So as you can see, the DMAC or the direct memory access controller consists of three registers: the address register, the count register, and the control register. So the CPU initializes the DMA by sending the information as follows: the starting address of the memory block where the data is available to read or where data are to be stored to write. It also sends word count, which is the number of words in the memory block to be read or write. Next, it sends control to define the mode of transfer, such as read or write. Lastly, it sends a control to begin the DMA transfer, and the information are sent through data bus. Okay, now let's have a look at direct cache access. So what is a direct cache access? Direct cache access, or DCA, allows a capable input and output device to place data directly into the CPU cache, reducing cache misses and improving the application response times. This process only concerns last level cache. In some systems, this will be a level 2 cache. In others, it could be a level 3 cache. So why do we use direct cache access? First of all, the direct memory access or DMA is not able to scale to meet the increased demand due to the dramatic increases in data rates for network input and output. So what kind of demands are we talking about? The demand is coming primarily from the widespread deployment of 10 gigabit per second and 100 gigabits per second Ethernet switches. Not only that, it also comes from Wi-Fi in the gigabit range. Here are some cache-related performance issues. Network traffic is transmitted in the form of a sequence of protocol blocks called packets or protocol data units. The lowest level protocol is typically Ethernet, so that each arriving and departing block of data consists of an Ethernet packet containing as payload the higher level protocol packet. The higher level protocols are usually the Internet Protocol or IP, operating on top of Ethernet, and the Transmission Control Protocol, the TCP, operating on top of the IP. This is the continuation for the cache-related performance issues. The Ethernet payload consists of a block of data with a TCP header and an IP header. For outgoing data, the Ethernet packets are formed in a peripheral component such as an input-output controller or a network interface controller (NIC). Lastly, for incoming traffic, the input and output controller strips off the Ethernet information and delivers the TCP and IP packet to the host CPU.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afidanian, and I'm going to present about the I/O channels and processors. So I'm going to present about the evolution of the I/O function. As computer systems have evolved, there has been a pattern of increasing complexity and sophistication of individual components. Nowhere is this more evident than in the I/O function. So we have already seen part of the evolution. The evolutionary steps can be summarized in the below diagram. Okay. First, the CPU directly controls a peripheral device. This is seen in simple microprocessor control devices. So next, a controller or I/O module is added. The CPU uses program I/O without interrupts. With this step, the CPU becomes somewhat divorced from the specific details of external device interfaces. And next, the same configuration as in the step 2, but step 2, the I/O module is added, but now the interrupts are employed. The CPU now need not spend time waiting for an I/O operation to be performed, thus increasing its efficiency. Next, the I/O module is given the direct access memory or DMA. It can now move a block of data to or from memory without involving the CPU, except at the beginning and the end of the transfer. And next, the I/O module is now enhanced to become a processor in its own right, with a specialized instruction set tailored for I/O. The CPU directs the I/O processor to execute an I/O program in memory. The I/O processor now fetches and executes these instructions without CPU intervention. This allows the CPU to specify a sequence of I/O activities and to be interrupted only when the entire sequence has been performed. And the last one is the I/O module has a local memory of its own and is in fact like a computer in its own. With this kind of architecture, a large set of I/O devices can be controlled with minimal CPU involvement. A common use for this architecture has been to control communication with interactive terminals. The I/O processor takes care of most of the tasks involved in controlling the terminals.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So I will continue the presentation. So I will explain about external interconnection standard. So from here we can see there are nine most widely used external interface standards that will support the I/O. There are Universal Serial Bus (USB), Free Wire Serial Bus, Small Computer System Interface (SCSI), Thunderbolt, InfiniBand, PCI Express, SATA, Ethernet, and the last is Wi-Fi. So firstly is Universal Serial Bus, or we call it USB. USB is widely used for peripheral connections, and it is default interface for slower speed device such as keyboard and pointing device, and commonly used for high-speed I/O, including printers, disk drivers, and network adapters. It controlled by a root host controller and has gone through many generations. So if we look at here, from 1996 until 2019, it has gone through four generations. And the first generation, the full speed rate is 12 megabits per second. But right now, USB 4.0 in 2019, it has full speed rate about 40 gigabit per second. So the second is the Firewire serial bus, or also known as IEEE 1394. It has been developed as an alternative to small computer system interface, or we call it SCSI, to be used on the smaller systems. The goal is to fulfill the growing need for high I/O speeds while avoiding the bulky and costly I/O channel technology designed for mainframe and supercomputer systems. And Firewire serial bus use a daisy chain up to 63 device connected. It provides hot plugging, which is to connect and disconnect the peripheral without having the power, and provide automatic configuration. So next we go to Small Computer System Interface, or we call it SCSI. It is a collection of specification for physically connecting and exchanging data between computers and peripheral devices. So in smaller system, USB and FireWire has surpassed it in popularity, while high-speed version remains popular for bulk memory supports on business system. So next, physical organization is a shared bus which can support up to 16 or 32 devices depending on the generation of the standard. So it provides parallel transmission rather than serial, and the speed range from 5 megabit per second on the original version to 160 megabit per second on SCSI 3U3. So next we go to Thunderbolt, one of the famous and fastest peripheral connection technology developed by Intel and Apple. It combines data, video, audio, and power into a single high-speed connection. It provides 10 gigabit per second throughout in each direction and 10 watts of power. So next we go to InfiniBand, a high throughput low latency computer networking communication standard used in high performance computing. So it released in early 2001 and enables servers, remote storage, and other network devices to be attached in the central fabric of switches and. So next we go to PCI Express, which is a high-speed bus system for connecting peripherals of a wide variety of types and speeds. It is the standard motherboard interface for graphic cards, hard disk drive host adapters, SSDs, Wi-Fi, and Ethernet hardware interface in personal computer. So next we go to Serial Advanced Technology Attachment, or we call it SATA or Serial ATA. It is an interface that links host bus adapters to mass storage devices through a computer bus, and it provides data rates up to 6 gigabit per second with a maximum per device of 300 megabit per second. So desktop computers as well as industrial and embedded application make extensive use of this application or use this technology. So Ethernet is a thing that we commonly use in our days right now. So, what is Ethernet? Ethernet is a family of wired computer networking technologies commonly used in the local area network (LAN), metropolitan area network (MAN), and wide area network (WAN). So, it became crucial for supporting PCs, workstation servers, and vast data storage system in both big and small enterprise. It has developed to enable data speed of up to 100 gigabit per second over distance ranging from a few meters to 10 of kilometers, and has moved from bus-based to switch-based. Right now, we can have internet system with rates up to 100 gigabit per second. So other than Ethernet, we use also Wi-Fi or a wireless internet connection technology that most widely used and can link PCs, tablets, smartphones, and other electronic devices such as video cameras, TV, and thermostats. So in the business world, it has become a vital tool of increasing worker productivity and network performance. The IEEE 802.11 committee has been able to produce specifications for new version of Wi-Fi at faster speed as antenna technology, wireless transmission methods, and wireless protocol design have improved. So recently we have received the most recent version of Wi-Fi, which is 802.11as, or also we call it Wi-Fi 6E, which is the maximum transfer throughput is 9.6 gigabit per second. So next, I will explain to you about IBM Z Enterprise EC13IO structure. So in IBM Z Enterprise EC13, it has 6 channel subsystem, and each channel subsystem it has four sub channel sets, and each sub-channel set it has up to 64,000 channels per sub-channel set. So under the channel subsystem, it has logical partition, which is it has 15 partition per channel subsystem, and it has 85 partition for whole system. So this is the IBM Z13IO system structure, where it has PCIe IO drawer and drawer 0 and drawer 1. So today we have learned so many things about input and output, and my friends has explained more about external device, I/O modules, programmer I/O, interrupt driver I/O, direct memory access, direct cache access, I/O channels and processors, external interconnection standards, and the lastly is IBM Z Enterprise EC13IO structures. We hope you can get something from this, and thank you for hearing us. Assalamualaikum warahmatullahi wabarakatuh.